Thank you very much for this opportunity to present Dr. A.G. Bhole Endowment Lecture. I personally think that I'm really honored and blessed to have this invitation. I also learned that many of its students are in attendance. So I thought it would have been appropriate for the students to present this lecture, but I was told that they have already spoken with basically other time. So today I'm going to talk about occurrence of Per and Polyfluoroalkyl Substances in drinking water, mapping, monitoring, and mitigation. I'm not sure very many of you have heard about the PFAS, and polyfluoroalkyl substances, except for probably a few scientists from Navy and those who are tracking down the emerging contaminant of concern. But this is really a big concern right now. As of today, PFAS has become a tremendous human health concern, and there's not a whole lot of research currently underway in India. If you search Google Scholar, you will not find many studies on occurrence, distribution, fate, transport, studies on PFAS, even though it's such a big human health concern worldwide. So with that said, I'm going to start with my lecture. So this is the general outline. I'm going to talk about what these substances are, what we mean by Per and Polyfluoroalkyl Substances. So I will just give you cursory introduction, a little bit of chemistry, so that will help you to understand why these chemicals, why these compounds are persistent, and why we should be worried about their long-term persistence and human health concern. And then we will talk about the evolution of regulatory protocol, like how we are dealing with the scenario once we realize that PFAS are everywhere, what we have done so far. And then followed by the final step, that's the maximum contaminant level, the primary drinking water standards that are enforceable standard, just like I think Bureau of Indian Standard, right? So your drinking water is regulated by Bureau of Indian Standard, BIS. In US, we follow the National Primary Drinking Water Standards, which are maximum contaminant level. So we can track down the history all the way to the MCM. And then I will talk about the monitoring studies. When we realize the tremendous human health impact because of these compounds, what has been done? Okay, first we would like to know the extent of contamination. How much, how big of a deal is this before we even start thinking about mitigating the problem. We would like to know how severe it is. So, in that regard, I'm going to share with you some granular studies, some of the distinct areas of the state of California, particularly the Orange County. I will also talk about San Francisco Bay Area and the whole state of California. And towards the end, I will talk about existing technologies, what has been done so far, and what is currently underway. So with that said, here is the timeline for PFAS. These PFAS were introduced in the 30s and 40s, and they became commercially available late in 50s. Some of the typical properties like oil repellent, stain resistant, waterproof, heat-proof, and their persistence. Okay. They became hugely popular and became widely used in all industrial and consumer products. So that's the whole genesis. Everybody was super happy. I mean, most of you probably have used the PFAS coated cookware. Some of you may be having omelette. You remember the non-stick cookware? Those cookwares are coated with Teflon, the miracle pan that was introduced back in there. So in 1956, the Stanford University finds that the PFAS binds to protein. So that was that understanding. It started right there. And do you know how long it took us to realize and come up with the enforceable maximum contaminant level? 2024 March. Think about it. So it's not that even though we realize that there is an imminent risk, imminent human health concern, yet for reasons unknown to us, we cannot enforce the regulations. Okay, we cannot promulgate the regulations. 1965, DuPont. Probably some of you are already familiar. Bayer, DuPont, 3M. These are the major players that manufactures the PFAS. 1965, 1978, PFAS, chemicals used to make DuPont Speclon. In 1978, I was barely in diaper at that time. Started my PFAS journey right there. Okay. So, despite all of this, nothing has been done. So, that was the timeline from inceptions to today. Okay. As I mentioned, the enforceable drinking water standard just came in March 2024. Okay. So the obvious question is, what is PFAS? These are PFAS are per and polyfluoroalkyl substances. Per, fully saturated. So you have alkane, carbon hydrogen chain. You can replace all of the hydrogen with fluorine. Okay. Typically, we are looking at a long chain C8 PFAS. Fully saturated means all except one where you can have the functional group. Okay. So that's what it is said. Polyfluoroalkyl substances, some, not all, are saturated with fluorine. So any PFAS, it will have a standard moiety with CN, F2N plus 1. That's an anion. You can see the charge. Obviously, you will attach the functional group to get the whatever the PFAS you want. So all the long chain PFAS, sulfonic acid greater than 6 carbons, okay, and then we have long chain perfluoroalkyl carboxylic acid. Those are the two primary main groups, and it will have 7 or more carbon, fully saturated with fluorine, except for the functional group. And so these are the two most common PFAS. PFAS perfluorooctane sulfonate and then perfluorooctanoic acid. These are the two most commonly detected. Even though these are phased out, okay, when we realize that there is a tremendous human health concern, 3M, DuPont, all these companies, they voluntarily phased out the production of these compounds. So then your question is, so where these are coming from? Well, we are dealing with the legacy contaminant. It's the past sin that we are now dealing with. So this is for the students. So this is how probably you can recognize how you can nominate a PFAS or give name to a PFAS. So there is an example, PFX. PF will always stand for perfluoro. X is the carbon chain length. So you have butane, 4, pentane, 5, hexane, octane, nonane, so on and so forth, and followed by the functional group. So you can now, if you ask me, do I know the name? I don't. I will go back to this table and figure out the name. Okay. So there are thousands of these compounds out there, so it's practically impossible. And here are some examples: butane, 4, and then there is that name perfluorobutanoate. Okay, so you can have the sulfonate and carboxylic group, and so you have C8 carbon chain. In fact, the name C8 is so common that they came up with a study like C8 health risk study itself, just by giving the chain length. These are some of the short chains, the chain length. So, how does it matter whether you have 4 carbon fully fluorinated and if you have 8 carbon with fully, what difference it does make? It's very important. Chain length determines their persistence, how long they will be stable, whether they will be bioaccumulating, biomagnify, bioconcentrate, persist, degrade, depends on the chain length. So even among the same group, sulfonate and carboxylate group, they have different tendencies to bioaccumulate. In summary, if you ask me, just give me a general statement. Well, these are hydrophobic. Okay, these are hydrophobic and lipophilic compounds, period. So, this is how the chain length affect. Short chain PFAS are more water soluble, like carbon chain length below 6. Okay, these are more. Again, whenever we see more soluble, it means more mobile than, because then it can be carried easily, less bioaccumulative. Typically, hydrophobic compounds are more bioaccumulative, typical, traditional. We started long back in DDT, PCP, and so on and so forth. So short chain PFAS difficult to separate. Now, why we are talking this? If you want to treat your water, all of this information falls in place. Okay, which PFAS you are dealing with, so that you can choose the appropriate water treatment technology. Long chain PFAS are less mobile, tend to bioaccumulate, move significantly greater distances, and long environmental health risks. So the chain length is very important consideration when we are talking about the PFAS, their environmental behavior, their persistence, their bioaccumulative potential. Alright, so then obvious question is, tell me the big picture. How big of this deal is? You can see the US map is almost littered with people. They are everywhere. Okay. This is just a US picture. How does the world scenario looks like? As I showed you in the very first slide, that we realized back in the 50s that these are toxic, potentially carcinogenic compounds. Okay. Yet we continue to use this product. Even today, these are the clean statistics. I can't read it from there. But these are some of the statistics that tells you how much amount of PFAS even today, at this point in a worldwide, is being used. We haven't stopped. Now you may say, well, there are alternative PFAS. Yes, the Gen X compounds, they were proposed to replace these more traditional PFOA and PFAS. Initially, they thought the Gen X compounds are benign. But after a few years, they realized they are the same problems associated with them as well. So we are back to square one. Obvious question is where we are, how we are being exposed to. So you can see this slide that shows all the consumer products, including your chocolate wrappers, food packaging, everything has some level of PFAS in it. Okay, so anybody who is using, in fact, let me give you this example. In the United States, more than 300 million people live. Okay? They were searching for a sample, pure blood sample, that is uncontaminated with PFAS. Do you know how many samples they collected? They find 0. The only sample that was pure blood uncontaminated with PFAS was that of a soldier who fought during the Second World War. So, all of us, including myself, all of us, in our blood model, we have these compounds. Okay, we are dealing with them on a daily basis. Even today, many of us who are sitting here in this audience, they are currently being exposed to PFAS this very moment. The cosmetics, all of these products. I'm not sure whether you can read it correctly, but you can see the slide down there. That's actually a graph that tells you like what type of lipstick, mascara, all of those products have PFAS in it. My question is like, our skin is porous, okay? I don't understand about the makeup, but there is this foundation that covers your pore spaces, and then you apply something on top of it. If you are applying something to your skin, which is porous, you are essentially sending those chemicals to your bloodstream, right? My question to you is, can you take these things and eat it then? What's the difference? Fair and lovely. Right? I mean, can you do that? Is it not the same thing? I mean, just hypothetical scenario. The skin is porous. We have skin permissivity factor. It tells us at what rate certain compounds can migrate through your skin. Period. So if that is the case, if it is going to end up in your bloodstream, it's equivalent to having a spoonful of Fair and Polyfluoroalkyl, is it not? But these are the scenarios, and there are products, like this is one of the major studies, how we are being exposed to PFAS. Now I am bringing this because we started out with just water. It's cumulative hazard, okay? It's cumulative risk. This is